And so it's truly a great pleasure to come here. I think I've been to Paris a few times. This is the first time to your university here, and I'm glad to give 3 lectures. Although I got a little bit of nervous. I'm pretty good at giving talks, but when I was told that when I give these talks, not only there are researchers, but there's also a bunch of vice presidents will be here. Well, I got very nervous about. Because usually you assume vice presidents don't know anything, right? No, I'm kidding. But seriously, that this is meant to be a kind of a pretty mathematical talk, but I try to make it less mathematical. I want to get the message itself is actually quite intuitive. Basically, all my students know that I keep telling them, in life, there's no free lunch, which means that it's for it, or you may have paid for it, or maybe you will be paid for it at some point. The reason I want to mention this is there are lots of scientific research. Oh,
that's okay. There was a pop-up on the screen and I had to remove it.
It's going to happen again.
No, it's not the same one. Another one.
Okay. Oh, by the way, there are people online, right?
Yes, that's what I'm at.
Hi for other people online. If you have any questions. Do they have a way to shop to?
Yeah.
Okay.
I think we can make sure that there are more questions.
Okay. Just all right. That'd be good. And the reason I mentioned this sort of a no free lunch or no free dinner, whatever you want to call it, is that lots of scientific research, either in statistics, mathematical physics, anywhere, that you're typically in a situation that you have to compromise. You can't just get everything, all right? And I think this is particularly true for all the vice presidents. Whatever you do, you can't just say, I want everything, the best, and I want to also have them the lowest price, it's just not possible, okay? And sometimes these impossibilities that you can actually establish mathematically. One of the probably the most famous one is the Heisenberg uncertainty principle, and I don't know how many physicists are here. Any physicists here? Oh, now I'm in trouble. Okay, 2, great. Well, you guys correct me if I'm wrong, but the general understanding here in a layperson is that you can't really try to measure a particle's position and speed precisely at the same time. Okay, and I want to show you later that there is the inequality, and mathematical inequality tell you just can't do that. All right, it turned out that a mathematical inequality, and for those of you, how many of you are mathematicians? Oh, I'm in the right crowd. Okay. So you all probably should understand. If you don't tell people, otherwise they're not mathematician. There's a Cauchy inequality, right? Okay. Essentially, the Cauchy inequality tells you you just can't do that. So eventually we'll see that this Cauchy inequality appears in multiple places. They all point to this kind of impossibility theorem. But my job, I'm not a mathematician. I was a mathematician. I was a pure mathematician trained at Fudan University. You might have heard about that university. And I was doing abstract algebra, which I love. But now I'm a statistician. So my job here today is really to give you the statistical interpretation of these uncertainty principles. Okay? Particularly this one, which I think I'm the one to point out. I wrote this article. I'll tell you a little bit of history of this article. Is in machine learning, and now, okay, how many of you here, you will probably call yourself a machine learner? All right. Wow, this is a great group. All right. The physicist is doing this. Okay. In machine learning, as you know, that a lot of things is try and error. Right. You have some ideas, you do simulations, you use the data, you do try error. When you try error, sometimes you just not necessarily know where is the boundary. Okay, so the one thing I always emphasize, say the distinction between an professional, like professional statistician, or an amateur statistician is not like the stuff that we do. It's like the stuff we know we shouldn't try. A professional will tell you, do not try this because it's impossible. An amateur will keep trying, right? Why not? Because I may be able to improve it. So this uncertainty principle, particularly the one I want to talk about in statistics, is called the Cramér-Rao lower bound, or the Fisher information bound. Those are the things we tell you, don't try. You can't possibly do better than that. All right, I'm going to make that connection between these two. There's a very similar results essentially saying in machine learning, which people have been surprised, which leads to this article. But I'm going to tell you what how to formulate this. I guess I don't have to apologize too much since you have lots of mathematicians there. That there'll be quite a few formulas coming out. All right. Since you are a mathematician now, I give you a job to figure out if there's any typos there. Okay. I'd be very impressed to say, oh, this should be purposely plan something there. Who knows? But so this article was really, if I can advance this, like this. Okay, how do I advance this? It's not listening to me. I need help here now. Let me say that this article was almost like a commissioned article. Let me do this. Okay, this doesn't work. Let me go back. All right. So this article was that I don't know how many of you recognize Xiao-Rao. If you're in statistics, you probably know who Xiao-Rao was. Oh, he lived for 102 years. To very recent. This is just a year before he passed away. He was given the International Prize in Statistics. Statisticians, we always complain that we never get Nobel Prize. What we do is we create our own prize, which is not really Nobel Prize. We have like maybe $20-some. But whatever, they actually give to Xiao-Rao, which for me was like, oh my God, this guy, he deserves every award. It's like we're just giving him so late. Anyway, so he did get it, but then unfortunately he passed away. So that because I've been editing Harvard Data Science Review, one of my co-editor, Rama Mukherjee, she's the professor at Yale University, and she was organizing a special issues in this Indian journal called Statistics and Applications, a special issue in memory of Xiao-Rao. So she invited me to write something because she knows that I've been working on a bunch of statistical topics, and every statistician you should be able to connect with Xiao-Rao in some way because he's done many things. And interesting enough that when she invited me, this is the problem with me that America was saying that I give people things to do, but I'm the one always get myself sucked into all kinds of tasks. When she asked me, I said, sure, I would write one without knowing how much time it's going to, I need to do this. And but the reason I wanted to do this one is because for years I suspected there is a deep connection between the Cramér-Rao low bound and the Heisenberg uncertainty principle. Okay, and I know the mathematics is just Cauchy-Schwarz inequality, but that's not a deep connection, right? Cauchy-Schwarz inequality can apply to so many things. That doesn't make the connecting just because we all use the same tool, right? But I know there's something deeper than that. And I wanted to look into it. I never had a chance to do it, or never really had an incentive to do it. I thought this will be the chance to, because I have to write up something. All right. So I get into it, but I actually didn't really realize how much I actually really get into it, especially because I knew absolutely nothing about quantum physics. I barely knew the Newtonian physics because I was a pure mathematician, in China. When I say pure mathematics in China, to my years, I was there from 1982 to 1986. I studied as a pure mathematician. I guess probably the French education probably can resonate. When we study pure mathematics, all our courses are truly just mathematics, right? Except a few courses on mandatory, physical exercises, the history of the Communist Party, these all mandatory course. I tell you that I took a course. The course, the title is Mathematical Equations for Physicists, right? Most people, at least in the US, would consider that's very mathematical. I had quite a few pure math professors ask me, say, why did you waste your time taking that course? Right. So that's how pure we were. The problem with that, obviously, my education was very, very narrow. Although after I become dean, I don't call narrow, I call it very focused. That was the real problem. But of course, when I'm doing this, I said, well, the little thing I learned actually is very helpful. So So basically what I set up doing that time was trying to make connection between the Heisenberg uncertainty principle and the Cramér-Rao lower bound. But it just happened, I'm going to tell you in, I think, the third slide, that there was an article just was published in JASA, Journal of American Statistical Association, and the article was reporting something seemingly very surprising. But when I look at, I realize, oh, that is just another version of this impossibility principle, and I'm going to share with you that. That's the one I'm going to make connection with machine learning. Okay, now because we have a broad audience here, so I wanted to remind everyone what does statistician do? How many of you will probably call yourself a statistician? Oh, that's very low. Okay, good. And you guys can correct me if I'm wrong here. And for the rest of you, you just haven't listened to me. Okay. So seriously, the one thing I talk about and I call the greatest statistical magic. Let me explain to you what does that mean. And in statistics, we pretty much do three things. Traditionally, we emphasize two, but because now machine learning, we emphasize the third. One is called statistical estimation. Okay, statistical estimation, probably the easiest way to explain is like the great examples, or maybe not so great example in the United States or other places, is you want to know how many people are going to vote for a certain party. All right, this is on everybody's mind, and you do this polling or surveys, right? You take a group of people and you find how many people voting there, and then you make what we call inference from that little sample to the population, right? Is estimating what is the population average. I'm going to use this example to tell you a little bit more, but let me finish the other two. That's called estimation. The other one we do a lot is called hypothesis testing. You already have a theory, or you want to test something. You want, for example, you want to know whether a medication works or not. You do those so-called clinical trials. You have one group get the placebo, the other group gets the treatment, right? And you compare these two groups. Then the hypothesis testing you're doing is say, assume nothing happens. What's the chance I can observe something of this nature? The whole idea of hypothesis testing is say you already have a theory. You want to confirm it, or you want to contradict it. All right. So that's called hypothesis testing. The one I think that gets really, really very popular now, especially for all of you do machine learning, is called prediction. Right? Now, prediction and estimations are very close. Okay, but there are some key distinctions there. Okay, one is the predictions. When we talk about estimation, we rarely talk about estimating an individual behavior. We tend to talk about estimating some population things, because estimating individuals is just not possible. If you think about it, it's hard, right? So typical step estimation is about some kind of population, some kind of aggregation. In predictions, we do try to predict individual behaviors. To marketing, to personalized medicine, today's lunch, we talk about personalized educations. We try to do that hard task, right? Now, the way you do it, obviously, I'm going to take a little bit more later, you make lots of assumptions, because if each individual is truly unique, there's not much you can do. But we make assumption that people's are, statistically speaking, there's the notion called exchangeability, which actually is quite a philosophical notion. How do I know people are similar to each other? What is similarity? What is the things we share? What are the patterns? These are the problems like starting from Plato, people worry about, right? The Platonic form. So you quickly become very philosophical to define what's individual. But the prediction is the game now. All right. The machine learning is pretty much all about a prediction. And you use label data, you use other things to check your prediction, to improve them, so on and so forth, right? The whole generative AI is pushed that in another front, because not only we predict, we actually generate, right? Once we learn the model, we kind of generate. But prediction estimation is it's not about confirming something I already know or contradicting something I already know. It's about to make an educated statement about something I don't know. All right. Now, one big difference between the machine learning culture and the statistical culture is statisticians, when we talk about statistical inference, we not only talk about estimating that quantity, we talk about what is the uncertainty in my estimation. That is a distinction between called a statistical estimation. Every time we talk about statistical inference, you can't write a statistical paper saying I'm doing statistical inference without getting an error bar or without getting a confidence band. The paper is going to be rejected. That then you say, what are you talking about? You know, you're just doing a point estimation. What's the error bar? All right? Okay. Now, in the machine learning content, I know we are increasingly trying to do uncertainty quantification, but it's hard. Many of you do it, you know how hard it is to do uncertainty quantification in the machine learning literature. But there is this notion there. But now here's the thing. If you really think about it, there's something quite remarkable in this claim that not only I can estimate something, I can also estimate the uncertainty in my estimator. That's quite remarkable. And I tell you how remarkable it is. Years ago, there was this late night show, the Jay Leno. How many of you heard of that name? No, a few Americans, Jay, right? So one day on his late night show, this is probably one of his most nerdy joke. Okay, he was, U.S. every 10 years we do, a census, counting how many people in the country. It's very controversial, okay, because the congressional seats, the federal budget allocation all depends on that, and the two parties always, argue with each other, and they want to do statistical adjustment. They say, well, there's an end count, but at the end count, the regions tend to be the ones with migrations, all the stuff, tend to be the more democratic. So you kind of got all the problem, even go to Supreme Court, all these things. But the reason I mentioned the Jay Leno, I thought that was a really interesting joke. I don't know how many people actually got the joke. He was saying, well, Census Bureau said they did a U.S. census. Then they report, they say, well, we have end count problem. End count problem because there are people they did not count them, right? And end count couldn't really jeopardize certain number of seats, depends on if the state has particular end count. But then he said, as a part of the joke, he said, I don't understand. But then they report we have 3% end count. He said, if we know 3% end count, why don't we just add it back? I don't know how many people would have even find that one was funny, but when he said it, I said, wow, no, that's interesting, right? What he said, like, how could it possibly, if you think about it, I said I have something end estimated, then I report I have 3% end estimation. Well, if I have that, I just add them up, then I'm done. So, but he's right? He's right in the sense like the Census Bureau, they did a thing, they know their end count, they have all kinds of reasons to believe it, they do demographic analysis, everything they know. But then how do they actually know how much the estimation is? If you are a decision maker, you do want to know what is my error, right? If the error is, say, 1 out of million, I'll say, well, nobody's going to argue that. It's not going to make much difference. If it's 3%, it could be quite a bit. But how would you actually know what that error is? Because if I know my estimator, if I know the distance between my estimate and the truth, then I can correct for it. Simple mathematics, right? The greatest statistical magic, and I'm really this big part of that's why I spend time on this. When the statisticians talk about the errors, we're not talking the exact error. Exact error is impossible. We're talking about the magnitude of the error. We're talking about the statistical behavior of that error, okay? And the statistical behavior of that error is going to be measured by something called standard deviation or variance. These are technical terms come in. These quantities themselves, when I say the error is 3%, I don't really mean that error is exactly 3%. But I do mean that we can calculate, statistically speaking, I can calculate all these with sort of reasonable assumption that the error is not going to be, the exact error is not going to be 10%, or the chance of that would be very small, and the exact error is not going to be, minus 3%. You could overcome, right? That gives you a kind of anchor point to roughly get a sense, which is very important for all the decision making, right? Any vice president doing the decision makings, you always have some uncertainties, but you want to get a rough idea, right? Are we going to be is our budget going to be shorter for like 20% or it's 2%? That will make a very big difference, right? Okay. So the greatest magic here, and I'm going to tell you where the magic comes from. how can statisticians or statistics can estimate something at the same time to claim that I know what is even roughly what the error is. Where is that magic come from? Okay, and we're talking about estimating everything on the same data set. All right, in the same data set, I want to get the estimator, but I also want to get error assessment. Now, here's something you have to think about. The ideal situation is say, well, I want to get the best estimator and then get the best error assessment. Okay, that's what we want the best. And this impossible theory or the uncertainty principle will tell you you can't really do both best. And I'm going to quantify what that really means. Okay, so now imagine the following. Okay, so this is a kind of a stat 101, right? I stole this from a textbook used years ago called Statistical Sleuth. I really like the title because it's all about a detective job. To me, and to many of you should think about, anytime you do statistics, it's essentially like being a detective, okay? Trying to figure out all the things, like where things could be. This population, right? Suppose there was a study on the called a twin discount on the schizophrenia. So the idea is they were trying to study, say, if you have one person in a twin has this mental disorder, does that necessarily, because they are twins, right? Do you think the other one has these problems? So they want these studies, and the twin studies are always really quite interesting. And you collected these natural twins, so on and so forth. One of my students now actually working on a problem is like the database, I think it's from Netherlands, say they are twins, but it's actually not quite clear whether they're twins or not. The twin status tend to be self-reported. There's a problem with that too. Okay, so there's all these data quality issues, which I'm not going to get into it. But think about this. This particular study, they were measuring some organ in the brain. They measured their size, and they were trying to look at that. If I can get measurement from the twins, and one has the disease, the other one doesn't, like do this brain part, that the difference in their size is what they call statistically significant. Okay, that's what they're trying to do. Now, what they did is they gathered this thing, right? Now imagine that in this population, this is called a population. Imagine you had everyone in this population, like all the twins you can study. Look at this volume difference that you get a distribution, right? Typically a histogram. Just see how many people had that kind of difference, right? How many, the mu here is saying that the center of the distribution, we typically call the mean. That's what we're trying to estimate. Like on average, what would be the difference in the volume in terms of this order, okay? But we don't really have that. What we have is we can take a random sample, right? Okay, assuming it's a random sample. In the sample, let's say we have a way to measure these differences, okay? So now you get a difference, like, there's the difference of some of 9, this is minus 1.9, this is 0.6. So you have all these numbers. When you have all these numbers, you can take the average. In this case, average is about 0.2. You can also do the standard deviation. Okay, standard deviation is just a measure of how things spread according to the average. Let's say in this case, the sample size is 15. So from there, you get one sample, right? When you get one sample, you can estimate the average is 0.2, and we probably would all agree. If that's all I have, I'd be pretty much estimating the population. Like my best estimate based on my sample is 0.2, right? That's called a statistical estimation. But the thing is, I want to know that how does that average, if I did a sample again, but that was 15 particular, right? If I did it again, that average is going to move a little bit, but how much will be these movements, right? And that's essentially get the variation concept. But here's the real problem. The problem is you only have one sample. You have 15 people there, but when you take an average, there's only one average, right? Okay. The one average, you have the one standard deviation. That standard deviation is not about how the average deviates from the population average. That standard deviation is simply saying in this sample, how each individual deviates from the sample mean. Is that clear? Right? So this part is the one, it's very easy to understand. That is how you trying to estimate the thing. But here's the problem. Ideally, what I want to do is, if I can sample it again and again, I will get different means, and I want the distribution of their means. Right? Because if I know the spread, on how the sample mean varies, this is the one always get students initially gets very confused. Anytime you take a sample, you do a mean, you got one mean, right? You take another sample, you have another mean. These means themselves is going to be all over the place. They have a distribution as well. What do we want to get hold on is what is the variability of that distribution? Because that tells me how reliably you can trust these means. Is that clear? But what I have is, I don't have the distribution of the means because I only have one means. What I have is a distribution of how each individual varies with its own mean. So the statistical magic is how do I connect these two things? One thing is what I want to know, how the mean is going to vary from the ones I can measure, which is how individuals vary around this mean for my sample. You make connection between these two. Once you make a connection between the two, you can do statistical inference. That's what I call the statistical magic. Okay? But the magic comes here not for free. This is the first no free lunch principle here. You need to make all kinds of assumptions. All right? The typical assumption you make, some of you probably ever heard about, is called the central limit theorem, which means everything in aggregate enough, there's a bell curve. That is one of the most fundamental, stochastic, probabilistic findings in the entire history. Okay, because that is analogy to basically said, although we don't know it's a spread, we know its shape. All right, that one is very deep, and you can argue about all the philosophical point why the nature even allows to discover such things. Why there's a precise mathematical formula to describe such things. It's all random phenomena, right? And that is absolutely fundamental. To this day, many things you do, you don't see it. They make the fundamental assumption called a normal approximation. Okay, so that's okay. So that's why pretty much. If you don't believe me, you can just do many things yourself. You will see the bell shape kind of stands out. Intuitively, it's pretty right. It's mostly in the middle, and the things kind of spread. Okay, so what we're trying to do is to find out what is this spread, how large the spread. So what is the fundamental magic here? Is on this second slide. What the series says is like, suppose you have a distribution of the individual and you have a distribution of the average. They basically have the two things that are very important. Number one, that if your procedure, like the average itself, is called unbiased, and as long as every sample can equal chance that is unbiased, these two distributions, they will have the same center. Okay? That's pretty intuitive, right? Average of individual and the average of individuals are the same. Okay, that's number one. The number two is the hardest one. Also, it's the most fundamental one. I know for all the statistician gets bored because we should move on. The fundamental thing is saying that as you have more and more average, if you make this assumption that these sample points are independent of each other, meaning they're not work together as a cluster, that spread, standard deviation, if individually is a sigma, let's say sigma equal to 1, as you average, the thing gets closer to the mean, but they follow the law of square root of n. That's so-called square root of n. You will see that all over the place, right? What that means that as n gets larger, eventually you become 0, right? As you should. But the thing is, this is actually not true at all. This actually even in Newtonian times, people did not know what the rule was. Why not n? Why not sigma divided by n? Right? There's a whole story about how Newton utilized this to his own advantage. You can read my colleague Steve Stiglitz article on this. It's a very interesting story. But if you do not know what the rule is, but eventually the mathematics, power of the mathematics, the central limit theorem tells you the square root of n law, which means it's very important. Which means that if you want to double the precision of your estimated, you need to quadruple your sample size, because that's a square root of n, right? But this is the magic. Why this magic? Because if I know the formula this way, n I know that's a sample size, and the sigma I do not know, but the sigma is about the individual spread of kind of means, and that I can estimate from my sample. Because if I have 50 people, I can have 40 degrees to estimate that sigma, right? Once I estimate sigma there, I can plug in here to get a rough estimator about the spread. Okay? That's a connection. Now you may say, well, why this has anything to do with observing principle, right? Here's the thing. you see that I have two things I want to estimate. I had the center to estimate the mu, I had the sigma to estimate, right? You see, well, okay, now the question is, this is a statistical job. What is the best way to estimate the mu, and what's the best way to estimate the sigma? For all the statisticians in the room, you should know, with the IID samples, we call IID, meaning the samples are independently, each sample with without interfere with each other, and identically, meaning they all come from the same distribution. You can show the best estimator. If you assume the bell curve, then it becomes what they call a maximum likely estimator, which means the best estimator. In this case, definitely it is. The best estimate mean is the sample average. The best estimating of sigma square, now sigma square, it's a variance, is this called a sample variance. Okay? So I just prepare you to understand that that's what everybody does. But you may not realize there is a really interesting phenomenon here. And this is the part I really want to show you. I hope nobody falls asleep yet. Other than sufficient, but it's okay. So now starting this mathematical notation, right? Think about these x1, n here sigma is 15, x1, xn is this difference in the volume in the brain organs, and the n notation is normal, it's a bell curve, right? They're centered around the mu. I don't think this works. Oops, that's fine. They're centered around the mu and have spread, sigma square. So what we do here is think about this is the maximum likely estimator, the best estimator, the sample average. Here is the actual error. Actual error is say the difference between my sample average and the unknown population average. That's the actual error, right? Okay. Now, here is the quantity. Here is the fact that we all use in statistics. We don't think what's the implication. Statistically, it's known that this average and the standard deviations, they're independent of each other. All statisticians know this fact. This is okay. The meaning is saying that these two quantities are independent of each other, right? And because independent of each other, you can construct so-called this T quantity. On top is the difference you want to study. On the bottom is standardized by the standard deviation, because remember it's divided by square root of the n. Remember that connection. So this quantity is so-called the T statistics, and it's the one that are used for T testing, for all kinds of stuff, for constructing constant interval. This is probably it's called a pivotal quantity, because this quantity itself, if you do the calculation, the distribution of this quantity no longer involves the mu, which is easy to understand because I've subtracted, but it does not involve sigma squared either. Okay, basically that becomes a free distribution. That's actually very important, because otherwise, anytime you do statistical inference, you do something based on something unknown, because when you ask you the unknown, if based on something else unknown, you get into an infinite regressor. Okay, which happens, which happens a lot of time. But here is the thing that we kind of textbook can never talk about, because this thing are independent of each other. Independent of each other basically saying, if you keep repeating this experiment, you will see this mu. Knowing the mu won't tell you anything about the sigma. That S, knowing something about S won't tell you anything about the mu itself, about X bar itself. So what this really tells you that what we think is the best estimator itself is actually independent of what we really try to estimate. Right? That sounds bad, because if I try to estimate something, at least you want to say, well, is the whatever I want to estimate and your estimate, are they have certain relationship, right? I hope that it's close enough. And this tells you it had to be independent of each other. Now that's where I start thinking, why is that? Why would anyone estimate a quantity by using something that is independent of it? Which independence is the statistical concept, which is saying they're not related to each other. How could that be? Well, that actually turned out to be a really necessary point, and the mathematical is going to tell you this is where the uncertainty principle comes in. Now, this is a paper I mentioned in Bates et al. In 2024. they were reporting the following phenomena. Lots of people say, well, that sounds like something wrong with the machine learning. They took a simple example. Actually, they took an even simpler. I'm using the regression example. Many of you are probably familiar with the regression idea, right? If I change one, how to change the other one, right? I want to estimate this theta, that's called the regression model. In the regression models, the least square estimator, which is estimated that slope, and that's called the least square estimator. And anyone who have done regression analysis, you know that estimate itself should be independent of what they call the residual. Residual is simply saying after I predicted according to this line, what is the arrows left? Okay, so these two things are independent of each other. Well, because these two things are independent of each other, and this paper basically reports that look, anytime we do machine learning, right? Lots of time when we do machine learning is we look at all the predictive errors and we use cross validation. Okay, many of you are familiar with cross validation. The hope is use cross validation to help me to choose what is best to predict, right? Okay, but what they show is that these cross validation errors, they are independent of the real errors that you actually care about. Okay, now that sounds like really, well, what I really care about is how my algorithms perform in real life, right? So there are these real errors. I want a real error to be as small as possible. Now, I'm estimating these real errors from these residuals, okay? But the mathematical theory tells you that these errors from residuals are really independent to the real errors, which means they could be anything. Yes, it could be anything. So why would it make sense for me to tune the model according to these errors that are not really predictive of the real errors? Okay, so that's the paper, and they showed this happens with Bootstrap and MLC because they're all based on these errors. So there are really two questions here. Is the first is like, is this a surprising phenomenon? The second is, well, why seems to works, sort of, right? Okay. And this is where I came in, because when I saw this article, I said, that's just another example of uncertainty principle. And I'm going to explain to you what that means. But let me just tell you, my colleague, R. Dempster, who was the one who invented all the belief function, which is very useful thing for imprecise probability. And he basically called this kind of estimators, that the estimators are independent of the truth they want to estimate. He called it irrelevant. Okay, for good reasons, right? So the question then is like, why are we using irrelevant estimator to do all these modeling? All right, so now let me show you what really happens. Okay, now this is getting a little bit even heavier mathematics, but this provides the little theorem to say what happens. Then I'm going to make connection with the Heisenberg uncertainty principle. Imagine you use, anytime you do these cross validations or do any other things, when you track errors, you need to specify what kind of errors you want to study. And typically we use so-called quadratic errors, okay? That's by far most people use quadratic error because it comes with also orthogonality in Hilbert space. It's all the good mathematics, and also has this decompositions, also decomposition. It's all very nice. So imagine this. Suppose you have some what I call learner. So think about more broadly, statistical estimator, because we're thinking about estimation. Machine learning like called predictions. I'm going to combine both, whether it's estimation or whether it's prediction. I call them learner, right? Suppose you have these unbiased learner. Unbiased learner is simply saying whatever, let's say this is the quantity you really care about, and this is your estimator, but on average they get it right. That's what unbiasedness means. Okay. Now, and also think about this is and here let's say you have something is meant to estimating the errors. Go back to this one. Let's say this is meant to estimating like whatever the error in the assessment. Now, because let's assume these errors themselves is unbiased, because if I want to if I have a good algorithm, at least I hope on average my error will be 0, right? Otherwise, algorithm is itself unbiased. So suppose here are the two classes. This is the mathematical notation to write. Let's assume both are in the L2, meaning they can be all, you apply this quadratic formula, it's all fine. So these are all the estimators, these are all the error estimators. So here is the mathematical result to tell you why, if you want to optimally estimate your Q, then any unbiased error estimator had to be orthogonal to the real error. Had to be uncorrelated. Okay, so here's the results. Thinking about R here is L2 norm, right? This is like the risk. Okay, so this is how much on average the L2 risk of your estimator. This is the optimal one, like the best you can do. What you can show is the difference between them relative to this itself. This quantity essentially is statistical properties will call the relative regret. Regret basically said the term regret means I could have done better, but I didn't. So that's a regret. Okay. What you can show is that the correlation between the actual error and whatever you're trying to estimate, the unbiased error, that correlation had to be necessarily less than this quantity. So what does it mean is that if you want to use the optimal, if you estimate turn to be optimal, this is 0, meaning this correlation had to be 0. Okay? Meaning that if you want to use all your data, if you want to use the data all for estimating that quantity, then you have nothing left for assessing the actual error. Whatever you can assess is actually uncorrelated with the real error you want to assess. On the other hand, if you want to leave something, so this correlation is not 0, it will say you necessarily have some regret. Is that clear? I hope you can start seeing the connection with Heisenberg concerning principle. All right. Intuitively, it's very clear. I've got the data here. If I use all my data to estimate the best of information in the data for that quantity, I have nothing left to assess the errors. Because if there's anything left to assess errors, I could have used that to improve my estimate. Okay? And this results actually, for those of you in statistics, you may recognize this, and I'm going to show you in the next slide. This is the exact same proof to prove the following very classical results. Any minimal variance estimator, minimal variance unbiased estimator had to be orthogonal to anything has mean equal to 0. That's exact the same proof. Actually, mathematically or rather geometrically, it's very easy to understand. Okay, so this is the geometric picture. It's all the one Pythagoras theorem, or the Chinese call it Goku degree, right? That's the okay. So all the set. Imagine you have two estimators. Okay, this one I used this is another slide from another talk, but it's the same idea. Suppose you have some estimators based on what's called complete data. The other estimator is based on part of data, the part of observed data. And imagine these arrows, the length of these arrows, these lines are the arrow. Okay. So what you can show is that in order for, let's say, so if this thing is not perpendicular to this, if this is not a 90 degree, then I can, like this one, right? Because this is not 90 degree, so I can always find a linear combination, actually many of them. This is a linear combining these two by moving here, right? And so then this line will be shorter than that line. You can always improve upon it, okay? The only time you cannot improve is had to be orthogonal. That's all it is. The algebra is complete trivial, okay? The algebra is complete trivial to prove this results. But the implication is not. The implication is saying, and this is actually, all my students know that, you typically do those things. Why do you do that? When you do cross-validation, why do you do hold-out sample, right? You don't use the same sample, right? Because you know you can easily overfitting, right? There's all those things. But this actually really tells you that a lot of those things are, you know, the mathematics tell you, I mean, intuitively it's very clear, right? I can't just use the thing to do two things. You know, it's like this also things like that's why we, you know, government needs all the different bodies to check them. Right? It doesn't work well like you are self-regulating, right? You're self-governing, you know, it just there are problems there. You need something else. Okay, so what's the connection with the so this is the what I call no free lunch, right? The learning uncertainty principle here is that if we want to learn most accurately, then we cannot assess the actual error relevantly and vice versa, because we can remove the predictable portion of the actual error to improve the learning. If I can realistically estimate my errors, why not to use that? So you need to make you need to make a kind of choice. Now, this is in Heisenberg simultaneous. I'm going to actually draw. So far, I'm show you the mathematical equivalence there. Run a statistical. This. Okay. So this I asked the ChatGPT, say create some pictorial for me to illustrate a certain principle. And did a pretty good job. And other than the words are not really great, but the idea I think intuitively for people don't know quantum physics or don't need to know, you can just imagine that if you want to measure where the car parked, and if you want to measure the speed of the car, you want to when the speed of the car, you need the car to move. Okay, this is a very lay person's think about, which is it's kind of helpful. Except that there's one big problem. When I was writing the article, I obviously sent to my physics colleagues, and they were telling me, Xiao-Li, you don't understand. Okay, in statistics, you talk about there's a joint thing goes on, and then one goes, the other goes. But in quantum physics, and now I'm a real physicist there, you can tell me if I'm wrong. They say, well, we can't even think of a joint distribution, right? There's no such thing. There's no joint distribution thinking about the position and the momentum, right? So I said, well, I don't understand the physics, why that's not possible, but I understand the mathematics. So I look at what they've done in the mathematics, and I realized that there is a way to think about this particular problem. And I think that the one great thing I've learned in studying this part of the quantum physics is that realizing that physicists have this particular notion that called a wave function or the state vectors are not the ones that statisticians tend to even think about, right? When statisticians think about something random, we think about two ways. We think about something called a random variable, like X or Y, right? It's a variable that can be moving, okay? All we think about in terms of its underlying distribution, right? You give me a distribution, I can write a random variable. You give me a random variable, you tell me that I can have the distribution, okay? Now, distribution comes in two flavors. There's so-called cumulative distribution, and it's also called a density, right? Like the histogram you see is part of density. Quantum physicists think about something called a wave function, which is very rare, very weird for statisticians first time to look at. Essentially, it's like the square root of the density. All right, with some sign to it. All right, it has a complex object. So it took me a while. I'm still trying to understand what it is, but I started understanding why that quantity has something really interesting. But in this particular case, take a one-dimensional, very simple case. Think about a particle has a position and it has a momentum, and it's evolving over time. The way I understand it is that the physicists describe this particle, this whole quantum system. Let's think about just one single particle using something called a wave function, and the position density is this because the wave function itself actually is a complex value, the number, a function, and so it has these norms that essentially the square of that is the density. Right. This is the thing in physics, in quantum physics, you learn the basic. It would tell you that anytime there's a wave function to describe it, but at what probability I can observe the particle in a particular position, the probability will be given by this quantity. Okay. Now you can see already the probabilities comes with a square instead of the usual ones. But what is the momentum density? Well, momentum density will be given by this psi function, and this function, and again is in terms of square. But the relation, this is the part, the fun part. The relationship between the position wave function and the momentum wave function is different. They are the Fourier transform with each other. Okay, this part I think all the mathematicians probably understand the Fourier transform. If you don't understand, you can think about one is like the frequency, the other is one is in a frequency domain, or the other is in a time domain. And there's all these physical constants, particularly the Planck constant. My understanding is this is a measure of the kind of what's the word? How deep you're looking to the universe. Only at that kind of scale and higher, then the quantum phenomenon kind of showed up. It's always there. My understanding is just like that whenever you get enough particles, they behave like a regular system. You do not see those things. It's not like it disappears mathematically, but there is a level for which you can see them. So why these things are important? So basically, this says that the quantum physical system itself has given you mathematical to describe the density of the position and the density of the momentum. All right. It doesn't give you a thing to describe how the two things jointly do it. And in fact, the whole, my physics colleague would tell me, like, don't even think about the ever joint one. The whole idea is you can't specify joint one because the uncertainty principle. But nevertheless, they do mathematics. So how does mathematics work here? What's very interesting is in this literature is that they use things called operator and operator. Yeah, operator. You can think about them as a mathematical subject, or you can also think about them as real physical ones. For me, as a more trained as mathematician, I understand them as operator. So they have a position operator, they have a momentum operator. The position operator is very simple. The operator applied to this function, to the position function, is simply multiplied by the function itself. That derivative, momentum operator is by taking the derivative. By taking derivative with respect to position, now with respect to time. That's the part confused me. Still confused me, right? Because typically we think of velocity is against time. Okay, but this is and here the I here, by the way, is that the square root of the -1. It's a complex number, right? So to the key thing here is that these two operators, one is the position operator, one is momentum operators, they do not commute. All right, they do not commute. That's creating this whole thing. Now, but if you think about functionally do not commute, it's very easy, right? You multiply the function, then you take a derivative. It's very different than take a derivative and multiply by something. You can see these two operators do not commute. So for me, again, this is my training. Thinking mathematically all makes sense, but that doesn't mean I understand the physics part. But it's important, right? We all learn different languages. Okay, we can all approach those things from different, different perspectives. Okay, so now what is the key thing here? The key thing is here, and I'm going to show this connection. Because in statistics there's this notion called correlation, right? How two things move together. And when we define correlation, we define something called a covariance. Okay, covariance essentially is the unscaled correlation. It's simply saying how the two things move together. It's the way to define covariance is the expectation of the product minus the product of expectation, right? That's how the covariations. In the quantum side, you can define correlation as well, covariance as well. But you can see because the two operators they do not commute, their differences is not zero. Is this imaginary number? Okay, and that is creating that uncertainty principle. In the regular statistics, correlation of x y is the same as correlation of y x, right? So in the regular world, you don't see this. You will not see this demand. No, I'm doing on time.
I have about 20 minutes left.
Okay, great. All right. So this is the key thing to drive this whole thing. If you take the product of these two variances, the variance here, remember, we use the variance to measure the uncertainty, right? Okay. This tells you the variance in the position and the variance in the momentum. This is where the Coase-Schwarz inequality comes in. Okay. The product of them had to be bigger than or equal to the covariance of the two. But because the covariance, they're not symmetric, it's very easy to right. This is the difference between them. So now you can see they're bounded below by this Planck constant divided by 4. Okay, so this tells you these two things they cannot simultaneous to be 0 because their product has to be bounded below, right? Which means that when one's large, the other has to be small. One is small, the other be large. Well, that can be small, but if it's one too small, the other one has to be large. Okay, the way to think about it is think about a rectangle. You have a restriction on the area. The area is now 0. Then you cannot say I'm arbitrarily moving these two. Can I make both edges equal 0? No, you can't, because the area is that. So what's the connection with all these things? Well, it turned out that everything we did have this flavor. So let me tell you, the learning principle I just talked about, the machine learning things, is telling you that if you take the G as the if you take this guy is the actual error, this is your estimate error, the covariance between them is bounded above by this, and the so-called Cramér-Rao bound. We talk about the famous Cramér-Rao bound. Famous Cramér-Rao bound basically says, and for those of you, this part is slightly more technical. The Cramér-Rao bound basically said for any uncertainty estimate, for any estimate is unbiased, it doesn't even have to be unbiased, but unbiased the easiest the one. Its variance had to be bigger than or equal to 1 over so-called the Fisher information. And the Fisher information is really the variance of so-called score function. And for those of you who understand likelihood, the score function is the derivative of the likelihood function. And so the Cramér-Rao thing is basically said the variance of my score function and the variance of the difference, the estimation errors, they have to be bigger equal to this guy. And the same is here, right? So you can see it's all these. The key thing, they all have the very similar flavor. The key thing is said that if you have two things, if you have restrictions on how two things co-move, okay, as a lower bound, then you cannot have their own variability to be simultaneously arbitrarily small. That's essentially the mathematical statistical. That's the essential statistical interpretation of the uncertainty principle. The one thing is different from the statistical way, the traditional, even the machine learning and the statistical or the Heisenberg uncertainty principle. The one thing is a bit different is in the top the two, I'm strictly thinking about distribution of random variables. Okay. Here, remember the x hat, t hat, these are not a random variable. These are the vectors. These are the systems. These are operators. Okay. So the difference here is go to the next level. In statistics, you can use a joint distribution to describe something moves. In quantum physics, because you cannot even talk about joint distribution, you're talking about how two systems, or what I call mechanism. One is a position mechanism. One is the momentum mechanism. How this mechanism moves together. But in another way of thinking about it is the statistical way of thinking about it is more high resolution, and the quantum ones is because it cannot pinpoint. You're talking about a system together. It's like a lower resolution. But the idea, the statistical principle are the same, whether it's a two position or whether it's two individual entity or the two mechanism. If the restriction on how they covary, then you cannot measure each one arbitrarily precisely. Okay, and that's that. That is just the whole nature of the beast. So let me now give you a little bit summary. It turned out this actually happens not just in statistics. I will tell you in machine learning we have this learning uncertainty principle. In statistics we have the Cramér-Rao low bound. In quantum physics, we have uncertainty principle. But in information science, in fact, I was definitely not the first one discovered this, because actually later when I found out that my colleagues in Stanford, Denmo, the Prof, he actually wrote an article really years ago, talk about how the CI bound and the Heisenberg uncertainty principles are mathematical equivalent from the information theory. There's another whole branch called the information theory. studying the channel information, right? Entropies, like you can have these shows exactly the same principle. They even show that it's a different proof, very interesting, showing how the CR-Rao bound and that uncertainty principle, going through something called STEM uncertainty principle. But there's also this as a, let's don't forget that all those things are actually really has a strong philosophical underpinning or even debate. So when you talk about something like the Heisenberg uncertainty principle, philosophers will be debating about, is this things like whenever we say we cannot measure those things simultaneously, is that just a human's limitation? Is that a kind of epistemic limitation, or it's a metaphysical limitation, meaning such things in the nature cannot happen, right? And for humans, we have trouble to, especially for me as a statistician, because I'm good at thinking about things like latent variable, counterfactual, all those things never happen in real life. But I can conceptually say, oh, the thing has a distribution. What do you mean I cannot even conceptually think about that distribution? That's the thing that statisticians need to overcome. But I think if you're a physicist, you're probably coming not having that kind of restrictions. You're just thinking about, well, nature, nature is like that. But there's a great article. It's free. There is a great website called the Stanford Encyclopedia of Philosophy. I highly recommend if anyone interested in these topics. They get a really great people writing. There is this long article by these two individuals. I don't know how to pronounce the name, called Uncertainty Principle. Okay, you read it. It's really interesting. The whole history about all the debate going on to this day. It's not a settled debate, and it probably will never settle. Even among the physics group, people take all this one particular interpretation. I have another colleague who's now working on this in this area. He's actually claiming, he's a physicist and a philosopher. He's telling everyone, we don't need all these things. Just take the old good statistical probability theory, as long as you don't make a Markovian assumption. Well, some of you probably understand what that means. You let the time go to infinity past, things go. You can just explain everything, including what they call the quantum entanglement, interference. Everything can be explained through the regular probability. So he's working on that. He's just sending some articles, very, very interesting. But what I want to mention is this particular for students in the audience, that as a scientific researcher, sometimes the most interesting thing you study, especially if it's important, you really have very different perspective from different fields. So I would certainly encourage. I really benefited by reading this one. I still haven't finished it. It's very long, but the part I read it was very interesting, very, very, very inspiring. And even here, you right there, you already have 5 different fields. So basically, let me conclude. This was part of this talk was really written for my statistical audience. And again, I asked ChatGPT to create these pictures. The whole idea is that we statisticians have not really looked into these quantum things. Some of us, very few, not at all. Most people don't. And there's all the other stuff. I think we really should look into it. But at the same time, I said you should step out of your own comfort zones. But at the same time, don't forget your own root, because we contribute. Every field contributed because of our own, the whole framework, the series we developed. When I encourage my students to go outside the comfort zone, and I told them, like, I'm encouraging to go to outside zone, but I'm not encouraging to jump out of the building. Okay, you still should be thinking like a statistician, but integrate out, because that's how the division of labor, right? This division of the how or scientific thoughts, how do we organize together so every field can contribute. So if I have made any contribution here are the two. One is that basically remind everyone, whether you do statistical learning, machine learning, there is a mathematical formula to tell you can't do both simultaneously on one data set. It's a different story you have another data set, okay? Because then it has like take a same data set and you split the two, right? So it's all like a mathematical formulation of a common sense. Number two is that these kind of principles is not new. It's repeated, happen again. And we have beautiful mathematical tools to prove those things. And also mathematical tools is very beautiful because the Cool-Schwarz inequality I apply in different fields in different ways. Some was applied to the individual states, others applied to whole operator. But it doesn't care. I mean, the mathematics, those of you who particularly do more abstract But as long as this notion is there, right? No matter how you define it, you can define the space elements could be all kinds of things. As long as you satisfy certain axiom, everything works. Okay. So here's a bunch of references if you're interested in. And again, as I mentioned, I probably will start with the Stanford Encyclopedia of Philosophy. But that's the one is most readable. There's no formula into it, but it's not. It's the one that actually you probably will sleep on it because it really tells you we don't really know that much about the real world. Okay? So anyway, let me stop there, and I'm happy to take any kind of questions. Thank you very much.
Okay, thank you very much for the great talk. So we have time for questions.
Please, any questions? Don't be shy.
Yes, please go ahead.
Thank you for the talk. Do you know that to your knowledge there is other inequalities or equalities that exist in physics, quantum physics, or other that are directly linked with statistics or other math subject or science?
Oh, you're just saying, are there some other
Example of what you show.
Yeah. I would say plenty. Okay, plenty. For example, and how many of you are familiar with the whole microchip Monte Carlo? Right? No, you know the Gibbs sample, right? You know all the Gibbs model, everything. These are all coming from physics, right? Right? These are all the we do these days do lots of IC model, what do you call it? Potts model, all the spin models. These are very much coming, coming from physics. And there's also something. How many of you know there's a thing called nested sampling? That's a more recent, right? Nested sampling is really physicists invented, and the physics has done lots of those. It's very interesting, particularly in the computation side, on the Monte Carlo computation, because they do. You probably know the original so-called the Metropolitan algorithm is because these are from Los Alamos. They're really solving all the problems on nuclear, right? And they invented all the solutions because they have computing so much stuff, right? So they're creating all these algorithms. Statisticians made a lot of contribution by popularizing them, by adding a lot more kind of rigorous theory, all the ergodic theory, all the stuff, right? And so that is one great example of how we, different fields really kind of cross-fertilize each other. But I'm sure, there are many other examples. But I'm only aware of some of those. Yeah. Great question. Yeah. Any other questions? So, I want to hear from the physicists. I have two of them, right? Tell us what is the latest debate in this area?
I was just wondering if you are going to connect this to the privacy talk for students later today.
Oh, yes, very much so.
No,
Actually, that's a great reminder. In privacy talk, not private talk. In privacy talk, the no free lunch is the trade-off between the data utility and data privacy. And how do you quantify both? And I'm going to talk about that. I don't think that that's actually a great question. I don't think there's a one simple formula there shows you, other than, yes, there's the one because it's a variance, right? So I would specifically, yes, I'll be talking about no free lunch principle there. And that one that probably most people can understand. If you want the privacy, the best way to keep your privacy is don't put anything online, which is too late. I know you have all things online. And so, that's another great example. That's a really good one. Yeah. And that's what I would be emphasizing to them.
maybe an announcement for the room at 5:30. There is the privacy talk.
Any other questions?
I have another one. Maybe I don't know if it's. I think it's maybe a bad for So Cramér-Rao bounds holds for regular models, for instance. So you can extend Cramér-Rao beyond
Yes.
regular models with accelerated speeds.
Yes.
So what would be the equivalent of that in
Yes.
physics? What's the equivalence of the regular model? Where does the regular model pop up in physics?
That's a great one. Actually, I should add other slides just for you. There is another what I call the second CR bound. It's not a Cramér-Rao, it's Chapman and Robbins bound. What they do is, remember the way everything we do here is assuming things are differentiable. Right? For example, literally, there's a derivative here, okay? So we use remember I mentioned briefly, there's something called a likelihood function. Likelihood function is, how many people know likelihood function? All right, so I don't have to explain too much. Likelihood function is your ability, the ability from the data to distinguish different states. And that's a fundamental concept when we talk about differential privacy. The whole differential privacy essentially is the likelihood ratio, okay? But what if the likelihood itself is not differentiable? Okay? It doesn't have to be differentiable. Then you just can directly look at the likelihood ratio itself. You can take 2 points. You can just take instead of taking derivative, you take what they call the differential quotient, right? Finite differences. You take a function difference in the 2 point divided by differences, right? And then the second CR bound is the Chapman-Robbins bound. They derive a lower bound using these differential quotients, right? And then that one is actually the special case. If you're assuming things are continuous, you will go back to CRO bound. Okay, so there's the formula there. Now the great question then is, what's the corresponding to the physics? I don't have the answer to that, but when I imagine that any physical system, if it's not continuous, there are these jumping things, then the mathematics is there. So you could have you could have the bound, yeah, and that inequality typically is not that taught in statistics, which I think it should be.
We'll give it in lecture, the first lecture on statistics. We'll have a lecture.
Oh God, okay. I apparently attended the wrong university, I shouldn't come here. So you can really teach that in the first?
It's an exercise.
Wow.
We don't all do it, but it's a good exercise.
I see.
Yeah, we mention it.
I see.
Because I think it gives a lot of perspective on Cramér-Rao.
Yeah, and in fact, for those people who don't know, when I mentioned Chapman-Robinson, the Robinson is the same Robinson who created the stochastic gradient, stochastic approximation, which essentially is almost everything. Is the whole engine drives all the machine learning stuff. Yeah.
We'll have many other questions about the
Great.
first. Go ahead, yes.
For machine learning, when we have to learn again, we have to retrain the model. And for humans, for example, we have continuous learning. So how does this principle move this time, for example, to have continuous learning?
Yeah, so it's a good question. I'm sure the way I formulated was very generic, right? I didn't put the time component in it. But I think the general principle here is that if you are learning from the past and you are testing in the next example, then that's fine because these are different data. But you could be greedy. You say, well, okay, should I relearn just using this thing? Fine, that's fine. You can relearn, but then you need another thing to do to the test, right? You're basically just saying you should never use your own. Oh, the other way thinking about it is, in a way, this is almost like a justification for cross validation. Why should I? Cross validation, by the way, it's so popular, but its theory is not well understood. It does not. I'm going to challenge everybody in the room, especially you are Bayesian. What's the Bayesian principle for cross validation? Right, the Bayesian principle of learning everything because all the things learn. Why do I need separate data? Like that seems very intuitive, but this will tell you why you should separate data. Just you can't do both, right? But to explicitly putting a time component will be actually very interesting. In fact, you're right, because these Heisenberg principles, I'm talking about the really static version. I mean, there's really how the system evolved, right? There's a time component there. And now once you invoke time, you get into another deep philosophical debate. Like what is time? Does time exist? There's all kinds of interesting stuff there. Yeah, but great question. Yes.
As Markov chain Monte Carlo is mentioned, I'm wondering that in reinforcement learning field,
Yeah.
how should we interpret this inequality as we are not using data to train the model and we are sampling some strategies and actions and states from the environment?
Yeah, great question. Now, what you just reminds me that the way I wrote here, I said it's like a data. But these mathematical notation, it doesn't matter whether they're data or they're actually, say, an information system. Okay? There are only two kinds of information if you think about in real life. One is from the data, the other from whatever you call it, knowledge, base, you call it pride, right? But you can also think about that as the past data inform the human. So these are all those things, just very much like how I write the Heisenberg principles. I don't write them as a random verb. I write them as operator. And to make these quantity precise, to make the mathematical language precise, actually is not very easy, right? Even when we talk about data, well, it's not easy. What are the data? Think about what are data these days. Traditionally, we think about data are numerical values, right? These days, like, what are the data? Text is data, right? Image is data. Everything is data. So lots of mathematical mixing very precise is not easy, but once you can, the mathematics give you a very powerful tool to tell you what's possible, what's not possible. But it's a great one because there is a way to write those things. For example, through the prime, right? This is the basic way of thinking about. Unfortunately, this is the kind of the fundamental problem with the Bayes theory that not knowledge can always be represented by this distribution. The most ironical one, and one of the problem, what I consider this the problem with the Bayesian calculation, is you cannot model ignorance. That's actually really ironic. But without ignorance, like Bayesian without ignorance is like doing mathematics without zero. And that's having generated all kinds of paradox in Bayesian thing, because we do not know how to define what we call a non-informative prime, right? Complete ignorant. There's no such thing, okay? Any probability distribution you think about, any probability distribution tells you how one state probability versus the other. That means it's not ignorant. People tend to use things, say, let's assume uniform, that's ignorance. Uniform is not ignorance, that's lots of knowledge. Everybody equally, that's lots of knowledge. That's not so that's the kind of problem you may run into when you try to write the knowledge one. But that's the part of the work for lots of one of my board member, Xiao-Li Meng, he's a philosopher, but this kind of stuff, kind of mathematics that he does is even more than I do, because he's trying to do these fundamental theorems, thinking about how to quantify knowledge, that kind of stuff. But that's another angle. It's very, very. Yes.
My third incentive principle is about physical system which we understand in our own social way, like humans.
Yeah.
And then you have another one which is more mathematical.
Yeah.
Information. And that's a problem, because one we can relate to physical system, and one which is just mathematics, which will just mold to any situation.
Yeah. Well, but that's the power of the mathematics, right? Because the system you understand, when a mathematical formula do the right, you feel like, oh no, that's great, right? You kind of help you to understand the mathematical language. You gain some trust of the language. But once you have to trust language, I tell the same language can apply to systems where you don't understand, but you gradually learn. Now it depends on who you are. I mean, physicists might find the quantum principle so easy to understand. For me as statistician, the Cramér-Rao bound is my bread and butter, right? And machine learners, you think of some other ways, but the mathematics as a common language, I think it is actually very, very important. Yeah.
Jamal, you have the last
Yes,
question,
Jamal.
maybe?
Last question. Okay.
Sure.
Thank you for the talk. You mentioned the work of Dempster on belief function
Yeah.
that he did with Shepard.
Yeah.
So and also imprecise probability.
Yes.
So do you
Yeah.
think that the same impossibility results hold also in this?
That's a great question. And I'm sure yes, but
Sure.
the form of that may be a bit more general.
Yeah. But
Yeah.
When we work with imprecise probabilities, we embed the uncertainty of the estimation in the framework.
Yes, and in fact, that I'm glad you mentioned that, because I was preparing to give a talk on imprecise probability, right? That's another field. There's
Which is a debatable framework,
Yeah.
by the way.
right.
Yeah.
Actually, the whole issue what I just mentioned, that Bayesian cannot do the ignorance. That's exactly
Yeah, that's exactly-
that's exactly
that's-
Dempster Shepard does. Yeah.
Yeah.
So that's another. Yeah. Well, maybe next year I come back and talk about that.
And I didn't grasp the idea behind, that you cannot commute the covariance. This holds when you work with, large stochastic matrices. This is known.
Yes, that's true too.
But-
Right, the two matrix stuff. So there are two ways to do operator in it. They
Yeah,
use
but
theory.
here we're working with the operator, right?
Yeah, but the operator you can just think about it as a matrix.
Yeah.
They have a
Okay,
one-to-one
but then
response.
there's the
That's exactly right.
cluster and all this.
Exactly,
that-
exactly right.
So there's a kind of a workaround to, you know, to
Yeah.
overcome this.
Yeah, you're right, yeah. There's a whole matrix version of
Yeah.
that. Yeah.
Okay, so I think we can thank Xiao-Li again.